Fortunately, Professor Wilkes gave me some more information that hasn't appeared in my research, so I'm going to read this one. He was born in England in 1913. He studied pure and applied mathematics at Cambridge University and did his doctoral thesis work at the Cavendish lab in radiophysics. During the war, he was engaged in radar and operations research, and when the war was over, returned to Cambridge to take charge of the mathematical laboratory, now the computer laboratory. He was responsible for the construction of EDSAC 1, which was working in early May 1949. Professor Wilkes was the first president of the British Computer Society, of which he is now a distinguished fellow, and was one of the group of consultants assembled by UNESCO to organize the first international conference on information processing in Paris in 1959. He helped to found the International Federation of Information Processing and was the British representative on the council of that organization until '63. During the period 59-60, he was the European member of the ACM Council. He became a fellow of the Royal Society in 1956. In 1967, he received the ACM Turing Lecture, and in '68 received the Harry Good Memorial Award of the American Federation of Information Processing Societies. In 1969, he was elected an honorary member of the Information Processing Society of Japan, and in 1974, an honorary member of the American Academy of Arts and Sciences. In 1977, he became a foreign associate of the National Academy of Engineering here in the U.S. He holds numerous honorary degrees. He was general chairman recently of the third Software Engineering Conference in May '78. With two colleagues, Professor Wilkes published the first book on computer programming, appearing in '51. Later, he wrote a book on automatic digital computers, and in '66, a book entitled A Short Introduction to Numerical Analysis. At the end of '68, he published the Time-Sharing Computer Systems book. He is the joint author of a forthcoming book, The Cambridge CAP Computer and Its Operating System, a capabilities-based system that was built at Cambridge recently and soon to come out. He is the author of a monograph on oscillations of the Earth's atmosphere. He has published many original papers in the computer field, including the formulation of the concepts of microprogramming, and then, to my recollection, the first paper on look-aside memories, which we now call which have become known as cache memories. So today he's going to speak on the birth and growth of the digital computer personal reminiscences. So I give Professor Wilkes.
An event which shaped the whole of my subsequent career occurred in the summer of 1946, when I received a telegram from Dean Pender of the Moore School of Electrical Engineering in Philadelphia, inviting me to a course on digital computers. The first ever to be held. Eckert and Maurice, fresh from their triumphs as designers of the ENIAC, were the principal instructors. Now, I was already in the computing world in a sense. When I was a student in the Cavendish laboratory doing radio wave propagation, I encountered a differential equation I couldn't solve, and I heard that there was in Cambridge a differential analyzer, a model differential analyzer, and I got permission to use it. That machine had been built at the instigation of Professor Leonard Jones, who was interested in the quantum theory of atoms and molecules. And he was a man of great vision. This was a model intended for propaganda purposes so that he could get the money to have a full-scale differential analyzer built according to Bush's plans, Bush from MIT. But instead of just saying he wanted a differential analyzer and a room to put it in, he said he wanted a computing laboratory. And that was, in fact, what was set up. At the last moment, they decided to call it the mathematical laboratory, an error that we had to correct some 25 years later. Now, of course, digital computers, as we now know them, were not even thought of then, and the idea of this laboratory was that it should specialize in analog machines and in desk machines. Well, plans were made to start this laboratory. Part of the anatomists, as it happened, had a new building. We were to have the old one, and we were told that if we opened the windows, the smell would go. But, Leonard Jones was appointed the part-time director of this laboratory, and I was the staff. And there wasn't any laboratory at that time, as I've said. Just as we were getting ready to open, the war came, and I went off to do radar and operational research, which I thought would be greater fun than staying around with differential analyzers. And after the war, I came back to Cambridge, and I found myself in charge of this laboratory, Leonard Jones having indicated that he didn't want to go on. And so there I was. I had a laboratory, and when this telegram came, I realized that I would be in a position to put to good use what I might learn on this course. I already knew something of what was going on in the United States. L.J. Comrie, had shown me in May 1946 a copy of a report drafted by von Neumann in which the principles of the stored program computer were laid out for the first time, report on the EDVAC. Now, one can speak perhaps more freely about von Neumann's role now than one could. He never claimed himself to have invented the stored program concept, and no one quite knows who did. But it came out of that little group at the Moore School, Eckert and Mauchly, and joined in a part-time capacity by von Neumann. But the great merit, I think, of Leonard Jones, of von Neumann, the great contribution he made was that he was on the side of the angels. He believed in the stored program concept. A very powerful person in those times was Howard Aitken, who had built the first automatic computer, which was a mechanical one, at Harvard. And as it so often happens, a pioneer in one generation will be reactionary in the next. And Aitken couldn't stomach the idea of the stored program at all. But as I say, von Neumann was on the side of the angels. And his prestige, which was enormous, was of great service, I think, to the computer field, or the few people who were interested in computers at that time. Von Neumann was never interested in what we would call now programming methodology. Mathematically, it seemed to him a trivial matter to program a digital computer. And he saw the computer as being used for very large jobs, a few very large jobs that would be programmed by experts, and really there wouldn't be very much programming to do. Well, I went to this course. Crossing the Atlantic wasn't too easy in those days. Shipping was still under government control, and I arrived rather late, but I attended the latter part of the course, and I got the full message, and a most generous sharing of technological know-how it was, most generous perhaps that has ever taken place. And so it happened that at the end of the course, I stayed on a little bit in Philadelphia, and I began to turn over in my mind the design of the computer that eventually became the EDSAC. I think I thought it would take about 600 vacuum tubes. It turned out in the end to take 3,000. Now, I was extremely lucky. I had many things in my favor. I was thoroughly confident in electronic design because of my pre-war work on ham radio and radio wave propagation, and of course experience of pulse techniques in radar during the war. And all that kind of thing seemed to me something that one could do. The new problem about a computer in those days was the memory. This was something that never, a requirement that had never arisen before. And there was one sort of memory that one felt could be engineered. That was the Mercury memory. One had a tank of mercury, in fact it was a tube of mercury, about 1.5 meters long, quartz crystals at each end, and the idea was to put pulses in at one end, wait a long time, a whole millisecond, till they came out at the other end, a millisecond and a half, till they came out at the other end, turn them round and clean them up a bit, put them back. Now, if one could make such a Mercury tank, then there seemed no problem, really, fundamental problem in engineering this device. No quantum mechanics or anything horrible like that. Good, straightforward, classical physics. And there I had another stroke of luck, because shortly afterwards in Cambridge I met Tommy Gold, who I think is now at Cornell. Now, Gold had worked during the war at the Admiralty Signal Establishment in England, and he had played about with Mercury tanks for the purpose of echo cancellation in radar. It was a technique that was never used in wartime, but it developed, work was being done. And he produced a design, complete design for a Mercury tank, and he said, if you make it like this, it will work. And so I did, and it did work. The only thing was that one tank wasn't enough, one needed a lot, and so I designed a battery of 16 tanks, and we had in fact 2 batteries. Between them they would hold 500 numbers, was the extent of our memory. I adhered religiously to the dimensions that Gold had given me. I didn't try to economize in mercury, which was an expensive item, by making the tube slightly thinner or anything like that. And this paid off. There was other work in memories going on. There was F.C. Williams, who had also been in radar, and while still in government service, he had conceived the idea of a memory based on a cathode ray tube. Writing, see, if a spot of light writes on the screen of a cathode ray tube, it will leave an electron distribution behind it. Of course, it leaks away very quickly, but if you can regenerate it, then you have a memory. We talked about these at the Moore School, and we thought you'd have to have 2 tubes to shuttle the information. But Williams showed that you could have a single memory, a single tube. But this all seemed very speculative and involved a lot of analog circuits and so on. So I was very glad to adhere to the Mercury memory. Now, the problems that faced the designer of a machine then, and remember no machine had been designed and built, I would say there were 3. First of all, there was a scale. If one designed with all deliberate haste, as one might a radar set or a television set, it would have taken 25 years. And Eckert had remarked, an lecturer at the Moore School before I got there, that the ENIAC had been designed in a considerable hurry. And the same was true of the EDSAC. One had to cut corners when something worked, accept it, and not look for the optimum solution. The next point was that a computer works with non-recurrent waveforms, whereas in radar and in television, the waveforms can be treated as recurrent, and if there's a sudden change, well then it's a flash on the screen, it doesn't matter. But in a digital computer, every pulse counts, and one had to be able to deal with transient situations. And thirdly, the problem of getting fast and reliable mechanical peripherals and their interfacing to the electronics. And I don't think it's always realized what a contribution the computer field has made to the design of mechanical equipment, fast mechanical equipment. The EDSAC was designed in a spirit of technological conservatism. For example, we chose a pulse repetition rate of 0.5 megacycle per second, where any electronic engineer worth his salt would have accepted the challenge of working at 1 megacycle, as most of the other people designing computers using this system did. But that conservatism, I think, enabled us to buy a little bit of time. Because our aim was to build a complete machine that could be used. We realized that building the machine was only the start of the project, that there was a great deal to be learned about writing programs, about how to use the machine for numerical analysis, numerical calculation, and all the rest of it. So the machine didn't have to have the highest performance of which the technology of the day might have been capable. It was a machine to have no luxuries. On the other hand, it was to be a user's machine, that is, easy to use, but that involved looking into a crystal ball because nobody had ever done it before. Well, we worked single-mindedly at this object. We didn't give any demonstrations of the parts of the machine on the way. We put it all together, and one day, on the 6th of May, 1946, the thing worked. It did its first calculation. And I think at this point, perhaps I might show you a few slides of that period. Well, that is a picture of the a battery of Mercury Tanks. You see the top row of tanks and the matching sections in the front. In addition to the big tanks for the main memory, it was necessary to have short tanks for holding single numbers in the accumulator and in other places. And that is a photograph of one of the short tanks. You see, the whole thing is about 6 to 8 inches long. That's a picture of one of the chassis, electronic chassis, that contains the complete equipment necessary for recycling the pulses in one of the Mercury tanks. Can you in fact see it? You can. Oh, that's fine. Good, yes. This is a photograph showing a group of people. The person kneeling in the center of the slide is Bill Rennick, who helped me to design the computer. And there you see some of the equipment is ready, that's sort of part of the way through the construction. Sorry, did I yes. And there is another rather similar picture when this construction was a little further advanced. That thing in the front is the power supply, which of course turned out to be wholly inadequate as the machine got bigger than we originally thought it would be. And here is a photograph of the computer taken shortly after it was completed. You see on the right a teleprinter used for output, a mechanical tape reader, which shortly afterwards was replaced by a photoelectric one. The main chassis. On the left, the memory, right at the back is the arithmetic unit. And finally a color slide showing the machine at a later stage of its existence. fault is wholly mine. I put the slides into the cassette. It is back to front. And I thought you might like to see this. The first entry in the logbook stating that the machine worked. And you notice on the second day, machine still operating. And it computed a table of squares several times, and that it attempted a program for computing a table of prime numbers. The program was found to be incorrect. It was, in fact, ran, I think, on the same day, though it's not recorded there. Now, having got the machine to work, the second phase of the project could start. And I remember calling together the programmers. Well, it would be wrong to, it would be an anachronism to describe them as programmers because there weren't any programmers. But calling together the would-be programmers, and I said that the initiative was now in their hands. The machine itself, for a basic input order, had the basic input instruction would read a single row of holes from the tape and put the corresponding binary number into the memory. And we used a special teleprinter code, a special punch tape code, which the figures were punched in their binary form. I think the leading bit was reversed so that we didn't have to ascribe a meaning to blank tape, which seemed an inelegant thing to do. Now, with that very simple input operation, in order that the machine should start to work, there had to be something in the memory to begin with. And so we had what would now be called a read-only memory with containing what we called the initial orders. The read-only memory was made of a set of telephone switches, stepping telephone switches, known as uniselectors. You pressed the button, the thing made a noise rather like a clucking hen. These switches went round, and the initial orders were placed in the memory, and control was sent to them. Now, it was David Wheeler that became the expert in this aspect of the subject. In fact, he became the expert in programming. I put it to him before the machine was finished that he might put himself in the position, imagine himself in the position of a man with a machine ready to go. What would he do about it? And he wrote the initial orders, the first set of initial orders, which would take an instruction punched on the paper tape in the following form. There was a letter indicating the function, the opcode. There was the address in decimal form, and there was a terminating letter, an S or an L, to indicate whether the reference was to a short or a long word, because in fact you could address half words in this machine. This was put in because the memory was very small anyway, and it seemed worthwhile. I might say the word length was 35 bits, and the half word were 18 bits. Sorry, that's not right, is it? 17 bits. And right from the very beginning then, we had initial orders of that sophistication. At no time did we do our programming in octal or hexadecimal or anything horrible like that. Now, there had been a good deal of talk at the Moore School about subroutines, and I had taken it for granted that a system of programming would be based on the use of a library of subroutines, so that you wouldn't have to write your programs completely from scratch. You would have these subroutines to draw on. As soon as we started programming and running programs, we found, to our surprise, that it wasn't as easy to get programs right as we thought it would be. You know, even the moon had to be discovered, and debugging had to be discovered. And I can remember to the exact instant where I was. Our tape equipment was on one floor, the computer was on the other, and I was passing down from the computer to make a change to my program tape. And at that instant I realized that a large part of my life from then on was going to be spent in finding mistakes in my own programs. But it gave a new importance altogether to the idea of a library of subroutines, because if one could have a collection of tested subroutines, then one at any rate would have a flying start. Not the whole of the program would have to be debugged. I don't know when that word came in. It certainly didn't exist at that time, but I use it. Now, it was about that time that Wheeler invented the idea of the closed subroutine, a subroutine which can be placed where you like in memory. It doesn't have to be placed in series with the program, and you jump to it and jump back. Idea now, of course, very familiar. And by the beginning of September 1949, he had ready to wire on the machine a new set of initial orders, which gave further facilities. They gave load time relocation, in particular, and this meant that you could have a library of subroutines ready punched on paper tape, so that you could copy these subroutines onto your own tape, and the initial orders would take care of the relocation. They would, in fact, act as a loader. I myself contributed what I called an assembly routine. This would take a set of subroutines, a main program, and sequences of numbers and working space, and put all these things together to form a program. And so what with my assembly routine and the initial orders, we had the rudiments, recognizably the rudiments of a modern assembly routine. And we built up on this basis a coherent system of programming. We set about writing a comprehensive report, and that was in draft in the summer of 1950. In fact, just before I set out on another trip to the United States. And the report was issued when I got back in September. Through the agency of Professor Kopel at MIT, that report was published by Addison Wesley, and the authors being myself and Wheeler and Gill, and that was the first book on programming. Addison Wesley were not the big outfit they are today. They were a little backstreet concern in Cambridge, Mass, and printed on a small rotary offset press. They were understandably a little suspicious about a book on programming, a go-ahead firm. You know, they didn't want to miss an opportunity, but they weren't at all sure that anyone was going to buy the thing. And so they proposed an unusual contract. There were to be no royalties on the first 1,000. There were double royalties on the second 1,000, and then normal royalties. So you see, they were protected against computer programming being, from the publisher's point of view, a complete flop. I'm glad to say that it wasn't very long before we were into the second 1,000, and I forget how many we sold, but it was entirely satisfactory. Now, in that book, were given the specifications of about 90 subroutines, and the full programs for about half of them. And there were some examples. And one of the examples was a program for computing the definite integral that you see there on the blackboard. This made use of 5 closed subroutines. There was a subroutine for integration using Simpson's rule. The integration subroutine needed an auxiliary subroutine that the programmer had to write for computing the integrand. And that auxiliary subroutine used library routines for the exponential function and for the sine function. There was also a subroutine for division because the EDSAC had no divider, and a routine for printing in decimal. So those subroutines from the library, together with the master routine, the main program, one had to write oneself, and the auxiliary which was written, these were nested 3 deep, 4 deep if you include the main program. And altogether, there were 300 instructions in that program, of which only 98 had to be specially written. The rest came from library subroutines. Now, you see, in a way, this was a kind of structured programming because it was based on nested subroutines, and nested procedure calls is one of the tenets of modern structured programming. Of course, it was long before the days of high-level languages, so that there were jumps of the ordinary kind within. One of the consequences of using this approach to programming, this structured approach, was that one did not have any need to use flow diagrams. And I have always felt that the motto on the banner of structured programming shouldn't be go-tos considered harmful, it should be flow diagrams considered harmful. If you need a complicated flow diagram to understand your program, it's not structured. And I was surprised that not everybody held the views we did about subroutines. There were quite a lot of people who didn't believe in this at all and thought that the program should all be written from scratch, and that the idea of a library of subroutines was a mistake. There's this example has one feature that at the time I was a little shy about, but now I can point to it with pride. The end of the integration was detected by the fact that the integrand had fallen away to a low value. And that fact, of course, was detected in the auxiliary subroutine where the integrand was computed. Now, I resisted the temptation to have a global jump back to the main program, but I organized an orderly return via the integration subroutine. Now, of course, that's absolutely in accordance with the modern principle of no global go-tos. At the time, as I say, I felt that I might be criticized for being a purist. This program, in fact, this problem was not in fact an artificial one made up for the purpose. It's an integral that I had met in 1937 in some work published by Sidney Chapman, on the ionization of the Earth's atmosphere by solar radiation. And I had conceived at that time a desire to tabulate this integral without any knowledge, any premonition of the fact that there would be digital computers and that I would be involved with them. And in fact, shortly after the book was published, I computed a table, and it was published in the Proceedings of the Physical Society. The next slide, that just shows a little bit of the programming, shows how that subroutine Q1, which is the integration subroutine, how it is called in. It's followed by 3 things which have a double line on the left-hand side. Those are the parameters of the call. The first one gives the current value of the variable, which is changed, of course, as the integration proceeds. the strip width and the upper limit of integration. Well, now, that was the summer of 1950. The book came out in 1951. And that was really the birth, if you like, as far as we were concerned, of the digital computer. Our friends elsewhere were making similar computers. They had one at Manchester. It was really designed, the drive there was, of course, the exploitation of Williams' memory. The computer was running shortly after the EDSAC, and other computers, the SEAC, for example, at the Bureau of Standards, came into action about the same time, shortly afterwards. And what I thought I would do now is to pass in review some of the main milestones in the development of the subject since that time. And of course, it's all happened really in a remarkably short space. When the events of which I have spoken were taking place, I was in my 30s. My scientific career had begun. I had published scientific papers. I was writing my first book. I'd done 6 years of war service. Well, even now, I'm not terribly old. So that the whole of this development, from the very beginning to the state we know it today, has taken place in just a part of a man's working life. Now, the great problem, of course, as I have said, was memory. And what really put the digital computer on its feet was the development of the core memory. At the Moore School, we thought the problem was on the way to being solved because Jan Reichman told us about the C-electron. And with what I later came to discover was his usual optimism, he explained that this device would be available very soon. And people made their plans. The Princeton machine that was being built in a unit by Bigelow, in a unit set up by von Neumann, was based on the assumption that C-electrons would be available. In fact, what saved the day was Williams' cathode ray tube memory. Williams used it in a serial mode, but in this country it was used principally in a parallel mode and appeared on a number of the early computers, and it really saved the day. It was a tricky thing to get going. There was a lot of analog circuitry in it. One was up against imperfections in the cathode ray tube screen, and so on. However, it saved the day. Now, the idea of the core memory was due to J. Forrester. And I remember, I think it was in December 51, I was over here, and I went to see the Project Whirlwind at MIT that Forrester was running. It was a very important and well-backed project. In fact, it did the development work for the SAGE air control system that came into action later on. I suppose Forrester built the biggest mini-computer you've ever seen. It was a 16-bit computer, quite simple in structure, all spread out. You could walk down the aisles between the digits. And Forrester had these ideas of a coincident current memory, and I well remember it. He took me to his home one evening, gave me dinner. It happened we were alone in the house, and after dinner, he began to tell me his ideas for the coincident current memory. And it gradually got dark, and we didn't bother to put the light on. We were so enthralled by this discussion. And I came away that evening asking myself, now, is this a pipe dream, or is this really going to happen? And of course, as we all know, it did happen. And the engineer who was principally responsible for making it happen was Norman Taylor. In the fall of 1952, I saw a 16 by 16 memory array working at MIT that Papian, then a graduate student, had made. In the summer of 1953, I came over here for a summer session at MIT that Charlie Adams was running. Now, I'd met Charlie Adams before. He belonged to Project Whirlwind, and his job was to administer a small amount of time on that computer that was being made available for academic purposes. And I found Adams a very kindred spirit. He absorbed the ideas that I offered about programming methodology, contributed to them, and so on. And he did a lot of pioneer work on initial orders of far greater complexity than we'd done originally, interpretive instruction systems, and so forth. By that time, the Whirlwind was working on an electrostatic memory, not the Williams type, but a type that had been made in-house in the project using special tubes. And this was working all right, but there were lots of parity failures and so on. Now, by that time, they'd built a 2,000-word core memory. And they'd built a special computer called the memory test computer for testing this thing. But it didn't stay on the memory test computer very long because it worked rather well. And so it was transferred to the Whirlwind. And I think it was transferred when I was there, or anyway, just before. I think while I was there. Certainly, I remember the shock, the thrill that ran through the group at the performance of this memory. And when I went home, I was able to report that there had only been 3 parity failures in 3 weeks, compared with a good many every day with the electrostatic memory. And so, overnight, the memory ceased to be the least reliable part of a computer and in fact became the most reliable. Moreover, the core memory held out the obvious prospect of having very much bigger memories. I might say that 2,000 16-bit words was regarded as rather a lot in that early stage. Not everybody, however, thought that large memories were a good idea. Von Neumann didn't. He consistently advised IBM, to whom he was a consultant, that it was a waste of money putting big memories on computers. The proper thing to do was have a little memory, a magnetic drum, and a good deal of ingenuity. And I think this idea was quite widespread. It's an example of the technological reaction that sets in. I remember at the same period going to see Reichman at RCA Princeton. Reichman had also been working on core memories, and he showed me a 100 by 100 matrix, that is 10,000 bits, that was working quite nicely on a demonstration setup, not on a computer. And I always remember this, that at lunchtime, Reichman suddenly became very serious, and he said to me, he asked me, did I think that programmers would ever really find a use for a memory of as much as 10,000 words? Well, I'm glad to say I gave the right answer, and I'm sure it was the answer that Reichman was expecting. But it does illustrate the fact that not everybody had the vision then to see that that was what was really wanted. Another thing I remember about that visit, there was a meeting of the ACM, then quite a young body, still had its meetings in universities and not big hotels. There was a meeting of the ACM at MIT. High-level languages were in the air. The term used was automatic programming. I know that term has recently been reused by our friends at MIT who are fond of reusing or misusing words, but then it meant high-level languages. And here again, there was a good deal of controversy. Was it a good thing? Some people said, instead of writing programs to write programs, why don't you all get on with writing real programs? Then we'd achieve more. and there was a debate held. I believe I was in the chair. John Carr spoke in favor of automatic programming, and I remember he divided programmers into two classes. There were the primitives, who thought that the only way to program was in octal or hexadecimal, and that anything else was a waste of time. And then there were the space cadets. And remember, this was a time before space travel had started. There were the space cadets who saw in the development of automatic programming the coming of a new and glorious age. Well, I wasn't a very impartial chairman. I hastily enrolled myself as a space cadet. Herb Grosch also spoke, and you'll not be surprised to hear that he was on the wrong side. Although he was afterwards converted and became a great advocate of automatic programming. I suppose one of the next big steps was the development of embryonic operating systems, the early batch programming systems. And this was a step forward because it improved the efficiency of utilization of the machine. You didn't have to have highly drilled operators hopping around to put one job on after the previous one had finished. The operating system did that for you, and it also enabled one, by the use of an auxiliary computer, to solve a great problem with early computers, the fact that the input-output devices were very slow, and this tended to slow down the machine. The idea of the early batch programming systems, batch processing systems, was that you had an auxiliary computer to load a batch onto magnetic tape, and then it went through, and finally a magnetic tape came out of the computer, and you put that on the auxiliary computer and printed. Now, this was fine for optimizing the use of the computer, but it was an utter disaster for the programmers, because you see, this strict batching using a serial medium like magnetic tape meant that a little job took as long as a big one. There was no hope of doing a short program test. You just had to wait for the whole batch to go through. And programmers became very, very frustrated at these systems that were coming in. Of course, a disk file instead of magnetic tape would have made all the difference, because then you wouldn't have had to have kept to the strict batch. Little jobs could have overtaken big ones. And indeed, in modern batch processing systems, that happens. For some reason or other, the word batch processing has survived, although there is no longer any actual batching. But the disk file was hardly there. I first saw one, it was the IBM RAMAC. I first saw it at the Brussels exhibition, International Brussels exhibition in 1958, when it was providing a kind of information service to tell you what year the American Revolution took place in, if you didn't happen to know, and similar things of a similar kind. You had to tell a girl what you wanted to know. She had to punch a card and put it in. Now, this led to a great revolution among programmers, and a movement grew up at MIT for the idea of interactive operation. MIT called it time sharing, which was again a reuse of a word which had a slightly different context earlier. I think the first real demonstration was done at BBN using, I think, a PDP-1 that had certain modifications done to it, and they demonstrated a system that would enable 5 users, I think, to use the computer simultaneously. MIT then set up Project Mac with the idea of developing the compatible time-sharing system. And I was lucky enough to be asked to go to the summer study that inaugurated Project Mac. And it was there for the first time that we had in our offices consoles connected to a computer. and that was obviously a wonderful breakthrough. It was very disappointing that the computer industry reacted against it somehow, except I think DEC, who were more forthcoming. But of course, that was the way things were going, that was the way things did go. We also had at Project Mac, we had another little computer, I think that was also a PDP-1, with a very simple display on it, a point-by-point display. And so we all played a bit with computer graphics, which was one of the next big coming subjects. And I think on one of my subsequent trips, shortly afterwards, I came to DEC. I think I came with Charlie Adams, who was buying a computer, and learned about the Type 340 display, which was the first of the displays driven on a cycle steering basis from a table in memory. And this seemed a frightfully good idea, so I went home, scraped together some money, and in fact we had one of the early Type 340 displays. It's still in running order. The PDP-7 was connected to Works. I think perhaps it really ought to be in the DEC Museum. It even has a spare cathode ray tube that we bought and have never used. But it ran for a very long time, and that started us off on computer graphics. Then, round about that time, a little later, computers and communications began to come together. The early computers, entirely freestanding. It's surprising, really. You may be surprised to know that before, I think it was 1964, it didn't occur to anybody to send data by wire. I put the beginning, really, of the modern interest in data transmission to a meeting that was organized by the Benelux branch of the IRE, forerunner of the IEEE, held at Delft in Holland. And I went to that, and I was so excited by all this that I delivered an impassioned speech to the British Computer Society called Data Transmission and the New Outlook for the Computer Field. We were very much concerned then about error rates of transmission lines. We realized there could be error control. We didn't realize how efficient and relatively straightforward it in fact is. Another landmark that I remember is the Spring Joint Computer Conference in 1970, when there were a group of papers about the ARPANET. That system, due to Larry Roberts, I think showed enormous amount of vision. Surprising how many decisions they took in complete darkness that turned out to be right. It gave rise to a new subject, that of protocols. I sometimes think that protocols best described as being a problem masquerading as a solution. And now, of course, we're very used to common carrier type of data transmission, and we couldn't exist without it. But there has grown up, much more recently, another kind of communication, wideband local area communication. Now, this owes nothing really to traditional telecommunications. It's something that has been developed by computer people using computer techniques. There are three systems you can use. You can use the Ethernet, and you can use rings of two different kinds, token rings or empty slot rings. They all give you much the same result. Now, if you have a local area system in your own building or on your own site, you are free from many of the headaches that beset the common carriers. You don't have the enormous investment of the past, you don't have the problems of compatibility, you don't have regulation. and you don't have the enormous capital problems that prevent newer technologies coming into telecommunications as quickly as we would like. And so I see in this development of local area, wideband local area communications, the real great sign of the sort of great thing of the future. It will enable us, I think, to develop distributed systems in which, connected to the same local area system, you have processors, you have file servers, you have hard copy servers, and all sorts of things. But I see Gordon's trying to catch my eye. He brought me here to talk about the past, and here I am babbling away about the future. Let me bring you back. Let me bring you back to the past by showing you the movie. And I would indeed request very strongly that those lights are turned out for this, because it's a somewhat dim movie. I'm sorry the room can't be darkened, but it was made it was the first computer movie ever made. It shows the EDSAC in operation. The commentary was, as you will see, recorded much later. I think perhaps I'll leave the film to explain itself, but please, before we show it, can we have the room as dark as possible? The film that I'm going to show you was made exactly 25 years ago. The EDSAC had begun to work in May 1949, and we had developed a system of programming based on the use of a library of subroutines. The film was made for the first joint computer conference held in Philadelphia in December 1951, and it was, I think, the first film showing the operation of a stored program computer to be made. Like all good amateur movies, this one tells a story. The parts were acted by members of the laboratory. I myself was mainly responsible for the scenario, and Eric Mudge, who appears briefly in the first scene, acted as the director. The film opens with Sandy Douglas, who played the part of a mathematician, explaining a problem to a committee of experts. The committee proceed to discuss how the problem should be programmed. In particular, which subroutines from the library would be used. Subroutines are a recurring theme, and in retrospect, the film might almost be taken as a commercial for subroutines. The problem is handed over to Stanley Gill, who played the part of a programmer. After it had been checked, it was punched onto paper tape and in due course run on the computer. While it is being run, we are shown a number of shots of the EDSAC, including some of the store monitor. Since these go rather quickly, I would like to give you some explanation in advance. The EDSAC made use of a serial ultrasonic store, consisting of 32 tanks, as we used to call them, each holding 16 words. It was possible to exhibit the contents of the memory on a cathode ray tube, like this. There are 16 lines, one line for each word. The presence of a 1 is indicated by a bright dot, and the presence of a 0 is indicated by the absence of a dot. An instruction occupied half a word, and at one point in the film you will see a program tape being read and the instructions filling up one of the tanks from the bottom. An instruction consisted of several characters, each punched as a row of holes on the tape. The rows were read under the control of the initial input routine, and the instruction built up in its binary form. This included the conversion of the address from decimal to binary. You will not actually see this happening since it takes place in one of the other tanks. What you will see is the instructions going into their final place in the store. I hope that this old film will give you some idea of what computing was like in 1951. I will try and give you a commentary as we go along. The mathematician explains his problem to a committee of experts. The first thing to do is to make a list of the library subroutines that will be needed. A subroutine for quadrature, one for the exponential function. A member of the committee interrupts to point out that there is a more suitable exponential routine available. A read routine and a print routine. The committee proceeds to discuss the programming of the problem. The programmer gets to work referring to the library catalogue as required. Here is the program sheet. The program is now checked and it is ready for punching. This is Margaret Hartree, who was my secretary at the time. She is in the course of punching the tape. And at the appropriate moment, she will go over to get one of the library tapes. This she copies mechanically onto the tape that she is preparing. The recommended practice, not always followed, was for a program tape to be punched twice and the resulting tapes to be compared mechanically. She finishes off the tape and takes it over to a comparator to compare it with the other tape. As long as the two tapes are identical, the comparator runs, but if there were a discrepancy, it would stop. She takes the tape to the computer room, attaches a tape ticket, and puts it on the job queue. Meanwhile, the EDSAC is running on some other problem, and the operator is waiting for the results to come out. Output was not quite as voluminous in those days as it is now. She puts it in the rack, takes our program tape, and puts it in the photoelectric tape reader. The instructions are being read and going into the store. The next tank. Now numbers are being read, and here you see the numbers in the store changing as the calculation proceeds. These are all short numbers occupying half a word. While the program is running, we are shown some shots of the EDSAC. The storage tanks are in a thermostatically controlled oven. Panels showing some of the vacuum tubes. back of panel wiring. A shot from above. The results are now coming out. This is one of the other programmers coming in for her results, but she must have made a mistake. We used to use for debugging a trace routine that would print the function letter of each instruction as it was executed. Our programmer collects his results. He is joined by the mathematician, and apparently all is well.
What was the approximate development cost for, say, the first 4 or 5 years, and how many people worked on the project in total at any given time?
Yeah, I don't know what the cost was. We weren't very good at keeping counts in those days. And, you know, universities don't do this in a very... I have no idea what the cost was. The group consisted of myself and Rennick, on the design side, 3 or 4 other people, and a bunch of assistants to do the construction, though most of the construction we put out to a small company. And then, of course, as soon as the machine was running, the people interested in programming, lots of people from various parts of the university got attracted in, and so the company of programmers grew fairly rapidly.
Did you ever consider calculating in decimal rather than in binary? And how did you determine the order code for your EDSAC?
Well, it was, of course, a controversy as to whether one should build decimal or binary machines. To a lot of people, it seemed quite obvious that the thing was to build a decimal machine. But to me, it seemed that the economy lay with a binary machine, that it was right and proper to work in the binary system, and that the conversion to and from decimal could perfectly well be done by the machine as part of the program. We were definitely on the side of binary systems. Eckert and Maurice, of course, who left the Moore School and went off to design UNIVAC 1, took the opposite view and built a decimal machine. The instruction set, well, we wanted it to be simple, minimum number of instructions, then I think and single address, again for simplicity, and then I think that doesn't give you too much choice. We had just over 16 instructions, I think, including a round-off instruction. Rounding off is the most important operation you ever do in numerical analysis. We recognized that fact and provided a special instruction for the purpose. In one respect, the EDSAC was wiser than its designers. There was originally a jump instruction, which I think jumped if the accumulator was positive, which of course is all you logically need. We had a meeting one day and decided it would be better to jump if the accumulator were negative. Well, somehow or other, when it was built, both instructions were there, and that was a great advantage.
When did you get the idea of microprogramming, and how did the concept develop?
So how did I get the idea of microprogramming and what?
And how did the concept develop?
Sorry? Oh, yes, I see. Well, after building the EDSAC, I was very conscious of the fact that what one wanted in a computer was regularity of structure. The EDSAC, of course, was a serial machine, but it was quite obvious that a parallel machine could be built with a great deal of repetition of parts, except for the control. which it appeared had to be done out of random logic. And I sought some way of arriving at a system of design for the control that would not be random. Now, one of the hints was the Project Whirlwind, which actually had a control matrix. And I remember standing in front of that and thinking about it. But the Whirlwind had to do no more and no less than 8 steps in the execution of an instruction. And you could, according to the diodes you put in the matrix, you could determine what happened on those steps, but you couldn't do any more. The addition to that, to make it into a fully flexible microprogramming system, was to make some of the steps conditional. And in fact, to set up microprogramming as an analogy with ordinary programming. The microprogramming was conceived as a result of a I definitely addressed myself to a problem that I saw existing.
What do you see as the greatest problem in the way of developing networks in the future?
Problem in the way of?
Developing networks.
I don't know. Well, I've already expressed my view of protocols. Protocols, yes. I just don't know how to answer that question. Tell me.
When you were designing the EDSAC rather, I'm curious as to, like you said, the choice of instructions was fairly obvious. Could you elaborate on that somewhat between all the instructions people wanted and what you felt you could do?
Oh, the instruction set again. Well, now let me see. One needed to be able to add something into the accumulator, subtract things from the accumulator, load the multiplier register to multiply, to jump conditionally, to shift the number in the accumulator left and right, and really that's about the lot, I think. Oh, there was a logical order that we called collate, which was the logical instruction of AND. There was one point that may interest you. If you're interested in the absolute details, we wanted to keep the number of instructions down to a minimum. And so we did not have a clear and add order, because that would have involved having a clear and subtract order as well. We decided to clear the accumulator on transfer. There was an order that would add into the accumulator, an order that would subtract into the accumulator, and 2 transfer orders. One would transfer from the accumulator to the memory and clear the accumulator, and one that wouldn't. And compared with the clear and add and clear and subtract, that saved an instruction.
When did floating point arithmetic start to enter the scene, roughly? Do you have any idea on that?
I'm sorry, it's awfully hard to hear the loudspeakers up here.
When did floating point arithmetic enter the scene?
Oh, I see. Now, that's a very interesting question. The relay computers, which preceded most of the electronic computers, had floating point. I believe some of the early Bell subcomputers, calculators, I think they had floating. And the relay people took that for granted. Now, the reason we didn't put floating point operation in the early electronic computers was that we just hadn't the courage. It was hard enough to build a computer anyway, and this would have been the last straw. And I remember being at, I think it was either Aberdeen or Dahlgren, where they were getting an electronic computer. They'd had the Harvard Mark II, which was a relay computer with floating point. And I remember them saying to me that they were going to find it rather awkward getting used to a fixed point machine. But you see, we whistled to keep up our courage. We said, oh, well, you can do it all with a subroutine. And in the book of programming for the EDSAC, you will find some library subroutines for doing floating point arithmetic. Slowed things down, but you could do it. And it's very curious. There grew up a feeling among programmers, among some programmers, that a floating point arithmetic unit would actually be a bad thing. They were afraid that it would be treacherous, that you would get cancellation of digits, and this would mislead you. Of course, you could have the same thing happening in a fixed point machine, but maybe you'd find out about it sooner. And so there was quite a strong feeling among programmers set in places that floating point was a bad thing. I never fell for that, and indeed, as soon as machines did appear with floating point, the idea just disappeared overnight. But it wasn't until the later vacuum tube machines, the second lot of vacuum tube machines, had floating point.
What error control mechanisms did you put into EDSAC to keep track of your dropped bits and failing vacuum tubes?
No, there were no built-in error detection. The idea was that the programmer should do that. There's one exception. There was one thing that the programmer could not check, as we realized, and that is that a number had been printed. And in its first form, it was possible to read back from the teleprinter the number that was being printed. But we soon got rid of that as not being very satisfactory and used a logical code, a 2 out of 5 code for output. And that gave us a check on the output. But there were no built-in checking devices. There again, it was hard enough building a computer anyway.
When the machine did become operational, what kind of mean time between failures did you experience?
Well, it was not a reliable machine. It was always going wrong. But somehow we got some work done. It's the nearest I can.
Were there any commercializations of the work, the Cambridge machines versus like the ones that were that was done?
Yes. Lands, who are a firm of caterers in England, ran a lot of tea shops. They were a very go-ahead company, and one of their executives was touring the United States and somehow went to Princeton and learned about computers and talked to Goldstein and said, well, you ought to go back home and talk to Wilkes. And they came and talked to me, and they gave us a little money. It wasn't very much by modern standards, but we were very hard up. It was a great gift. And they built a computer called Leo 1, which was a logical copy of the EDSAC. It was the engineering was gone over to a considerable extent, had Mercury tank memories, and quite a number of those machines were built and used. So there was a commercialized version of the EDSAC.
The input and output devices were a logical extension of what you had at the time, but did you give it any thought to any other input and output devices? Like, besides typewriters and printers?
I'm not sure I quite understand the point of the question. We had paper tape for input, and at the beginning we had a directly coupled teleprinter, but we soon replaced that by a tape punch for output. Is that? Perhaps you'd like to elaborate?
Yeah, but it was more along the lines, you were doing a lot of scientific computation with integrals and the like, and there was a long process of getting from the integral and the blackboard to getting it programmed and the like. So I was wondering if you give any thought of any other ways of inputting the problem that you wanted to solve.
No, I don't think so. No, I think we just did the simplest thing we could think of.
How much controversy at that time was there around the issue of word length? You were really made I think the first short word length machine It was clearly against von Neumann saying that things should be 40 bits.
Well, the reason we had 35 bits, that is 34 plus a sign, is that it's 10 decimals. That was the reason. And also, we wanted to have 2 instructions per word, and that is about the minimum word length that will do that. The actual memory bandwidth was 35 bits. I mean, it was really a 35-bit machine, but you could deal with half words. As we wrote it up, the easiest way to explain it was to suggest that it was a short word machine, and you could run 2 together. But that wasn't the way the designers looked at it.
What kind of debugging aids did EDSAC have?
Debugging aid software. There was one that the film illustrates but doesn't explain. There was an interpretive routine designed by Gill that would cause the computer to print the function letter of every instruction as it executed it, and on a transfer of control it would start a new line. This gave you a dynamic trace. We also had post-mortem routines which would enable you to see what was in the memory when the program was stopped. We had comparison post-mortem routines which enabled you to feed the input tape in again, and the machine would print only those locations that had changed. Printing was very slow, so that was worthwhile. Oh yes, and we also had checkpoint routines. You'll find all these in the book. Checkpoint routines whereby you could plant a jump somewhere so that whenever the machine came to a certain instruction, it printed out information that you wanted. But it was all software.
One thing that wasn't clear from the picture, if you ever ran out of space, memory space, writing your program.
Yes, but we were terribly
What did
short.
you do?
We were terribly short.
So what was the way out?
Well, you see, it was all so new, there were so many problems to solve that we only chose those we could manage.
What was the instruction execution speed of, say, an add instruction or a multiply instruction?
An add instruction took 1.5 milliseconds. A multiply, you have to have 2 instructions, loading the multiply register, which would take 1.5 milliseconds, and then the multiply, which took, I think, 4 milliseconds. I've forgotten something like that. I said, by the way, earlier that the tank delay time was 1.5 milliseconds. In fact, it was a millisecond. A very slow machine.
Was there a program to do optimum assignment, or did people do that on a hand basis?
No, I
Because
set
in
my
a
face
single
against.
instruction-
No, I set my face against that. It seemed to me that the Mercury Memory was a temporary measure anyway, and that it would be the height of folly to devote limited effort to getting round its difficulties. And so the machine was quite deliberately designed so that you could not do optimum programming. Well, a number of people did it. And of course there was an ad hoc argument for doing it, that if you could get more work through the machine, then perhaps you should. But it seemed to me to be wrong in principle, and never did it.
Did you ever develop programs that had overlays, say, on paper tape?
I'm awfully sorry.
Did you ever create programs with overlays on paper tape?
Can I hear you without the microphone? The loudspeaker's in the wrong direction.
Did you ever create programs with overlays on paper tape?
Overlays? What do you mean, memory overlays? Oh, yes. Oh, yes, we did that, certainly. You see, one of the advantages of having the initial orders in the memory, you could leave them there if you liked. You could reuse the space if you wanted to, but you could leave them there and jump back into them to read more from the paper tape. and that was quite common. You could even have the machine stop and the operator press the start button, reload the initial orders, read some more stuff in and carry on. Oh yes, certainly.
What were the power needs of this machine? How much current did it draw?
Oh dear. Well, I do know that that first power supply, which gave 250 volts, 10 amps DC, which we thought would be ample, was wholly inadequate. So the voltage remained at 250. I suppose it must have drawn about 30 amps, between 20 to 30 amps. We had slow switching for the vacuum tubes. When it came on, the vacuum tubes didn't come on quickly. They came on in stages. This was a precautionary measure.
How long did the machine stay in use? What did you replace it with? And what would you say was the most significant problem or difficult problem that was solved on the machine in a programming sense?
Well, the machine ran from May 49 to July 58. And by that time, there was some overlap with our second machine, EDSAC 2, which was also a vacuum tube machine using a core memory and with a microprogram. A much more powerful device with magnetic tape auxiliary memory and so forth. It was, in its last year, it was just kept on for benefit of people who had programs running on it, particularly X-ray crystallography. I don't know what the most significant thing was. It handled a vast amount of, I wouldn't like to single out. There was some stellar equilibrium stuff done, I remember. Just general miscellaneous. I can't think of what I would pick out as the most important. The most interesting thing that EDSAC 2 did was the calculations for the structure of hemoglobin that Kendrew worked on at the Medical Research Council unit in Cambridge. We did the reductions. Oh, and also for the servicing of the synthetic aperture radio telescope. That was done on EDSAC 2, though the initial experiments had been done on EDSAC 1.
I'm interested in finding out what you used to store the return address for your subroutines. I mean, you obviously didn't have something like a jump to subroutine as in modern computers. How did you, if you were calling a subroutine from several different places, how would the subroutine know which place to return to?
Yes. Well, this was Wheeler's invention, the Wheeler jump. What you did was to write an instruction, an add instruction, whose address, the address in it, was the address of its own location. So that instruction would add itself in to the accumulator. The accumulator was empty. This instruction would add itself in. And the next instruction was the jump order. The first thing the subroutine did was to take this instruction in the accumulator, add something to it to turn the add opcode into a jump opcode, and then it would plant that at the very end of the subroutine.
Were there any diagnostics in the processor itself, or when it went down, how did you get it back up?
Well, it is all very hard, is all I can say. Oscilloscope, test tapes, usual business. We realized, of course, the need for further advances in certain respects, that being one.
I recall you made a statement fairly early in one of the papers about the whole issue of investment in software versus the cost of the machine. And in view of that, it doesn't sound like EDSAC 2 was compatible with EDSAC 1.
No, it wasn't. No, we didn't follow our own advice.
How was machine time charged? By clock time or? Was it service to the university, or
How was it what?
how was it charged?
Oh, we didn't make any charges, no. We just let our friends use it.
Well, in fact, in that, in the movie there was this sort of batch place. Could you sign up for standalone time? How was it used as a time sharing? I mean, was it used as an individual,
Yes.
interactive personal computer? Was it a personal computer? I guess that's the latest buzzword.
Of course, you quite understand, don't you, that that was a movie telling a story. I mean, well, obviously it was life as it might be or ought to be, not life as it really was. Though for a good part of the day we did have an operator, in fact that girl you saw, running the computer. Because we soon found that if you let programmers run their own problems, then they weren't interested, as it were, in getting out of the way for the next man. And so that it was, in the interest of efficiency, it was a good thing to have the machine under the control of an operator. But during part of the day, there were programming tests. People could have the machine for programming tests. And during the night, it was entirely in the hands of volunteer programmers. But we definitely had the idea that it should be run exactly in the way illustrated in the movie. And to a certain approximation it was.